Welcome to AI Podcast. Today we're digging into a fresh AAAI 2025 paper called TimeCAP, and the headline is simple. Instead of asking a large language model to stare at a bunch of numbers and guess the future, the authors first ask it to describe what those numbers mean, then use that description to make the prediction.
So it's like telling the model a story about the data before asking for the ending. Who's behind it?
Geon Lee at CAST and Wenchao Yu at NEC Labs, along with collaborators, two groups, academic and industrial, teaming up.
Nice mix. Give me the elevator pitch. Why did they think this was needed?
Traditional time series models, and even recent LLM approaches, mostly treat the model as a straight predictor. You feed in raw signals or tokenized numbers and say, tell me if it'll rain or if the index goes up tomorrow. But real-world series are full of context. Think geography for weather, macro trends for markets, or seasonality in healthcare. If you don't surface that context, you cap what the model can do.
Right, the numbers don't explain themselves. So what's the TimeCAP move?
Two LLM agents plus a small trainable encoder. First agent, they call it AC, takes the recent window of data and writes a short, domain-aware summary, like a weather forecaster's note. Second agent, AP, reads that summary and makes the call. Then there's a multimodal encoder that learns a joint representation of the time series and the summary. It uses that to retrieve a few similar past summaries as in-context examples for the predictor, and it also makes its own prediction. Finally, they fuse the encoder's view with the LLM's decision.
So contextualize, augment, and predict, hence the name. Can you ground that with an example?
Picture New York weather for the past day. The contextualizer might say something like, humidity trended up while pressure fell. Winds shifted from west to south, which often precedes a front. That's a compact narrative the predictor can reason over. Then the encoder pulls up a few past cases whose summaries read similarly, little "this has happened before" notes, to anchor the predictor's judgment.
That retrieval bit sounds like showing the model annotated flashcards that match the current situation.
Exactly. And because those flashcards are text, the LLM is in its comfort zone.
What about the data and tasks? Where did they test this?
3 domains, 7 real-world datasets. For weather, hourly measurements from cities like New York, San Francisco, and Houston, with the task of predicting rain in the next day. For finance, daily indicators centered on the S&P 500 and the Nikkei, predicting if tomorrow's move is up, down, or basically flat. And for healthcare, weekly signals tied to mortality and test positivity, predicting whether a key metric will exceed a threshold.
So these are event predictions, not full numeric forecasts.
Correct. Classification tasks, not regression. That's a good fit for the tell me what's likely to happen next framing.
How do they actually run the models? Are they fine-tuning big LLMs?
The big LLM stays frozen, accessed through an API, think GPT-4 style. The trainable part is the multimodal encoder that blends the series with the generated text. For the text inside that encoder, they use a smaller language model like BERT, which they can fine-tune. That keeps costs and compute manageable while still letting the system learn a useful joint representation.
Got it. And comparisons? What do they stack this against?
Classic and modern time series models like PatchTST and TimesNet, plus LLM-based baselines such as PromptCast or GPT-4TS that use text prompts more directly.
All right, bottom line. Did TimeCAP actually help?
Yes. Across those datasets, contextualizing first and then augmenting with retrieved examples led to consistent gains over the baselines. The average bump in F1 score is around the high 20s when they use both contextualization and augmentation. They also highlight cases with much larger improvements, but the consistent story is that the text summary plus retrieval makes the LLM smarter about what the numbers imply.
That's a big deal because you're not forcing the model to reverse engineer meaning from raw numbers. It gets meaning in plain language first.
Exactly, and the ablations tell the same story. If you strip away the in-context examples or skip fusing with the encoder, performance drops. Each piece contributes.
What about data efficiency? If you only have a thin slice of labeled history, does this still hold up?
They tried reduced training scenarios, and TimeCAP kept more of its edge than the baselines. The intuition tracks. When labels are scarce, leaning on the LLM's prior knowledge and retrieving relevant textual cases is especially helpful.
I'm curious about interpretability. If a model says rain or no rain, do we get a why?
Two flavors. Implicit rationales, short, human-readable reasons from the predictor like rising humidity with falling pressure suggests an approaching front, and explicit comparisons, post hoc notes saying, this looks like those earlier days where conditions matched and it did rain. Those retrieved summaries double as explanations.
That's closer to how a forecaster talks to a human. Before we crown a champion, though, what are the caveats?
A few. First, dependence on a proprietary LLM API. That raises reproducibility, cost, and potential model drift issues. Second, code availability. The datasets and the generated summaries are public, but the multimodal encoder code is listed as available upon request, which slows full replication. Third, scope. The tasks are event classifications in 3 domains. Real deployments often need calibrated probabilities, cost-sensitive decisions, and robustness under distribution shift. Those aren't the main focus here.
And there's a subtle risk, right? If the contextualizer writes the summary, it might sometimes overinterpret a noisy signal.
Yes, summaries are helpful, but they're still generated text. The retrieval step and the encoder fusion help ground things, but teams adopting this should monitor for overly confident narratives and check calibration.
Let's rewind to the big idea for a second. Why does this work so well?
Because it plays to an LLM's strengths. LLMs were trained on text and world knowledge. When you convert a window of numbers into a concise, domain-aware description, the model can reason with prior knowledge, like what a pressure dip usually means or how volatility interacts with index moves, instead of trying to infer all that from raw sequences.
It's like giving a doctor not just lab values, but a short chart note that says, here's the trend and the context. The decision is still data-driven, but the framing is human legible.
Perfect analogy.
If a team wanted to try this, what practical advice would you pull from the paper?
Start by prototyping the 2-agent loop on your classification task. Make the contextualizer produce short, structured summaries, not essays. Train a compact encoder that sees both the series and the text and use it to retrieve a handful of similar past summaries as in-context examples. Keep the big LLM frozen to control cost, and build a simple fusion of the encoder's prediction with the LLM's output.
And on the research side, what's next?
3 things stand out. 1, repeat the study with strong, open-weight models to improve reproducibility and cost control. 2, stress test under distribution shift and add uncertainty estimates, because real data drifts. 3, extend beyond binary or ternary events to continuous forecasting and counterfactual what-ifs to see whether the contextualization advantage holds.
I'd add governance for the summaries themselves. A lightweight check that flags when the contextualizer starts making claims not supported by the numbers, or a calibration layer that tempers confidence.
Absolutely.
All right, quick takeaway for listeners who are running between meetings. TimeCAP shows that the shortest path to better predictions may be to pause and explain the data first. Let the model write the context, retrieve a few similar cases to ground its thinking, and then decide. It's accurate, it's more sample efficient, and you get rationales you can actually read.
Well put. If you work with weather, markets, or public health, and honestly many other domains, this is a pattern worth trying. Ask the model to tell you what the series means, then ask it what happens next.
That's TimeCAP in a nutshell. Thanks for listening, and we'll see you next time on AI Podcast.
See you next time.